Hello everyone. I'm Hao Yu Ji from Harbin Institute of Technology, Shenzhen. I'm excited to present my paper titled Language-Assisted Skeleton Action Understanding for Skeleton-Based Temporal Action Segmentation. First, let me introduce temporal action segmentation. It is an essential field in computer vision with applications in many areas. Its goal is to classify each frame of untrimmed action sequences. Based on the input modality, TAS can be divided into two categories: video-based temporal action segmentation, which uses video features, and skeleton-based temporal action segmentation, which focuses on human motion through skeletal data. Our research falls under the second category, skeleton-based methods. Currently, skeleton-based TAS methods mainly rely on spatio-temporal modeling to capture spatial dependencies among joints and temporal relationships across frames. These methods then generate frame-level one-hot classifications, which are supervised using cross-entropy loss. However, these methods have some limitations. First, graph or attention-based joint relationships struggle to fully capture semantic dependencies between joints. Also, one-hot encoding supervision fails to capture the similarities and differences between action categories. To address these challenges, we introduced language-assisted skeleton action understanding. We called it LaSA. LaSA leverages language modality to better model the semantic relationships among joints and actions. On the left, you can see how we implement language-assisted joint relationships establishment, and on the right, how we implement language-assisted action relationship supervision. These two approaches help capture the correlations and distinctions among joints and among actions. Our contributions are threefold. Firstly, LaSA is the first to use language-assisted learning for skeleton-based action segmentation, utilizing linguistic priors to enhance the understanding of joints and actions. Secondly, we establish relationships between joints using language knowledge, applying attention matrices and joint text-based position embeddings to model correlations and distinctions. Thirdly, we apply language supervision to establish relationships between actions, using contrastive learning with action text and clip text pairs to differentiate actions and uncover semantic links between adjacent actions. Our method significantly outperforms existing approaches, achieving state-of-the-art results. Now, let's dive into the LaSA architecture, shown here. LaSA takes skeleton sequences as input. After initial spatial feature modeling, it establishes joint correlations and distinctions through attention matrices and joint text-based embeddings. After the overall modeling, we apply contrastive supervision using action and clip text features to enhance action discrimination and correlation. The blue section represents the inference stage, while the green section shows additional components used during training. Next, I'll explain the language-assisted joint relationships establishment module. For spatial feature correlation, after multi-scale graph modeling, LaSA utilizes an attention matrix generated from joint text embeddings to integrate spatial features further. For spatial feature distinction, joint text embeddings serve as positional embeddings, highlighting semantic differences between joints, which enhances subsequent attention fusion between spatial subfeatures and temporal features. Then, the language-assisted action relationships supervision module operates at the action level, segmenting features into actions and clips based on ground truth boundaries, applying textual supervision. For action discrimination, we use contrastive learning with action text pairs to enhance action clustering and separation. For adjacent action correlation, we apply clip text pairs contrastive learning to improve temporal associations between neighboring actions. This module is only used during training. The overall framework includes two branches for action segmentation and boundary regression, responsible for per-frame classification and boundary prediction. Training involves using 4 different loss functions, as shown in the diagram. Moving to the experiments, we conducted evaluations on 5 public datasets: MCFS 22, MCFS 130, PKUMMD, XSub, and XView, and LARA, using frame-wise accuracy, segmental edit score, and segmental F1 score as metrics. In our quantitative comparison, we observed that across all evaluation metrics, our method consistently achieves state-of-the-art performance, with notable improvements in segment-level metrics, demonstrating the effectiveness of LaSA in action segmentation. The representation space visualization shows that LaSA creates a more structured semantic feature space compared to previous methods, better clustering intraclass features, and separating interclass boundaries. It also better distributes different actions, emphasizing the role of language in regularizing feature distributions. In qualitative comparison, our method results in fewer over-segmentation errors, class prediction mistakes, and boundary shift errors, producing outputs much closer to the ground truth. Lastly, our method also performs well in terms of efficiency, maintaining competitive computational costs while outperforming methods like MSGCN and IDTGCN. We also conducted an ablation study on our key modules, which shows that incorporating either mechanism from the two modules improves performance, while combining all four mechanisms from both modules yields the best results. In conclusion, we present LaSA, a language-assisted skeleton action understanding framework that uses language to improve connections and distinctions among joints, and to enhance discrimination and correlation among actions. However, some prediction errors remain, suggesting room for further improvements. Future work may focus on finer-grained motion descriptions for more detailed supervision. Thank you for your attention. This concludes my presentation.